Welcome to the project demonstration of PIC Microcontroller automatic power factor correction along with power factor display on Blynk app. So here we interface the CT and PT. So this one is a CT, current transformer, and PT. So from these two transformers we are going to get the current transformer waveform and voltage transformer waveform, which is on the load directly. Okay, so whenever as we know that if we use a R load, so then the phase difference between the current transformer and voltage transformer is 0, and then power factor is nothing but cos theta. So the theta is nothing, 0 nothing but it's near to be unity power factor. So cos 0 is 1, near to 1. So then if we add any L load, inductive load, in series with the R load, then the current wave and lags, and based on this phase difference occurred, then the power factor will be comes down to below 0.9 based on the L and R load. So based on this difference finding, and then microcontroller will take a decision of adding a capacitive load in parallel with this R and L. So with the help of relays, so it will switch on the one relay first and then check the power factor. If it is corrected above 0.9, then it will leave that, or else it will switch on the another relay and the capacitor will continue in parallel with the same R and L load. Then it will check for the power factor corrected or not. So as we demonstrate in this project with two different loads, one is 40 watts bulb, another is 200 watts bulb. So coming to this, these two are the potential divider circuits along with to detect the zero crossing of current transformer and voltage transformer, and this one is regulated power supply board in order to provide the 5 volts power supply to the motherboard of PIC microcontroller and 12 volts power supply to this relays, because we are using electromagnetic relays which can operate at 12 volt. And now remaining we are going to provide the extra power source for the node MCU, because it needs the more power. So it will upload the power factor value to the Blynk app, which is already stored with the authentication API key inside this node MCU. And the flow is, so current transformer, voltage transformer, and after that these two waveforms will be fed to the PIC microcontroller at A0 and A1 pins, and next the outputs are electromagnetic relays connected at C6 and C7, and the power factor value will be displayed on this 16:2 LCD. It is connected at B2 to B7 pins of 16F73 microcontroller we are using, and parallelly it will send the power factor value through serial communication to the node MCU from the B0 B1 pins. And here this is the reset switch, and this one is a crystal oscillator, so it will provide the 20 megahertz of crystal oscillator frequency. And coming to this relay board, so there is a one transistor, because the relay need 12 volts to get switched on, and the transistor will on by the microcontroller, means the microcontroller will trigger the transistor, and the transistor will trigger the relay, and relay will trigger the capacitors. So this is the way of controlling the relays and execution. So let us see the demonstration. Before switching on this kit, we need to initialize some steps in our phone. So that is, we need to enable the personal hotspot with the name of project 4463. This is the very important. So we need to enable the hotspot project 4463. All are small letters without any capital, without any space, and a password 123456789. And after that, enable the hotspot as well as enable the data also. Okay, we should on the both, and now it's on. And now after switching on that, so you can go to Blynk app and log in to the Blynk app directly. Okay, so you can see that one red mark is there. Now means the node MCU is not connected. So now just get the power supply to the node MCU as well as the bulb. You can see one device will be connected to your phone. You can see that one device got connected, and the LCD will display the power factor value continuously. Okay, and now go to that, the same power factor value will be displayed on the Blynk app. We can see that is 0.95, same 0.95 on the LCD screen. Whenever I added the inductive load, then it will check for the phase difference between the voltage and current waveform, and then it will take some time, because gradually it will checking for every 1 second, and the same data will be sent to the same Blynk app. So now the power factor comes down to 0.78, and now the microcontroller will take the decision to control the relays. So if is a malfunction, just you can restart this. Already the relay gets switched on, and now it's lagging. You can hear the sound, and because of the relay back EMF, the microcontroller getting restart, but it will be settled down. Right. So now gradually the power factor will be increased. Right, it's 0.86 now, and again it will switch on the second relay also. Right, and after that it will be settled down. And whenever I switch it on this inductor, because the inductor is connected in series with the R load, that's why it is the dimming, because of the voltage got divided in between these two. Now if I switch off this switch, and then this inductor will isolate from the R load, and then automatically the power factor will comes to the leading. Right, is leading now, because and now the microcontroller will isolate the capacitors from the load directly. So we can same demonstrate with this. Let us see the 40 watts bulb. Now it is only 40 watts bulb, and now if I switch on the inductor, so when we use the low wattage load, then it will take more time for execution and for calculation. We should provide some time to capacitor has to be discharged, though it's isolated. Right. So when I switch off this, it will get switched off, and it's corrected. When I switch off the inductor, then it will show the leading based on the right, and then the relay will be off.